Welcome to this example on electric potential difference calculation. Now, I am going to make the assumption that you do know what the electric potential difference is, and I'll put up a link up above there to the video that explains and gives you intuition on how to think about these problems. One item that I would want you to be comfortable with is when you take on these style of examples where you're just calculating what the potential energy change is, that's what the difference will be. In those cases, you should know what happens to charges as they move through electric fields. So please recall from that video that I pointed out, two items that you should know. Is that when you have a positive charge and it is moving in the direction of an electric field, therefore it is a loss, of potential energy. So it transfers most likely to kinetic energy when it's going with the actual electric field. If you have a positive charge and it's going against the electric field, then there is a gain of potential energy. So that's something that you should understand, and that's what that other video and link provides. And if you're dealing with negative charges, it does the opposite. Wow. Now, what is very helpful in understanding that and intuitively knowing what is happening is then you don't have this headache with this negative sign and thinking about what values, positive or negative, should you substitute into this equation. So that's why it's very crucial to understand the intuition to what happens to charges as they move through an electric field with respect to the definition of an electric field that you have, which points from positive to negative as you're going through. All right, so let's jump in and let's do the calculation, within here. So for part A, we have a charge which is moving against the electric field from a position of 3.1 meters to a position of 0.85 meters. What is the electric potential difference? Now, it doesn't matter how it's moving as long as you know if it's moving with the electric field or it's moving against the electric field. So that's something that you have to know. Now, our charge is 0.25 coulombs. It is placed in an electric field of 125 newtons per coulomb. So we have something like this. Again, it doesn't matter in which direction you point your electric field, but what you do have is you're moving your positive charge. So this would have been our positive charge within here, and you're going to be moving it against. All right. Now it's starting off, not that it matters. So 3.1 meters, and it's going to move all the way to 0.85 meters. So within here. So as you're going through, so you know you're moving against the electric field within here. Now this is your initial position. This is your final position. So you can certainly find out. I'm going to just take the magnitude of the displacement, within here. So that magnitude would be, 3.1 minus 0.85. And this is, I guess this is going to be 2.25 meters. If you want to do the final minus the initial, so then it's going to be a negative change, within there. But I'm just interested in the magnitude itself. Now, as pointed out, since this is moving against, this is going to be a gain in potential energy. So the difference will be positive. So I know that the actual potential energy difference, is indeed positive as a result. So I'm going to put a plus. And therefore, this negative right here is irrelevant to me because I do know that if I'm moving against the electric field, I am gaining potential energy. Now, if I am gaining potential energy, then all I need to know is just, what are all of the values? So 0.25, that's my charge. I'm going to make them all positive. 125, that is my electric field strength. And then I have my displacement, which is 2.25. So if I multiply all of these, I'm going to get the result. Now, again, keep in mind that I'm taking the magnitude of all of them because I already know that I'm gaining potential energy. If you're worried and you don't know, if you're gaining or losing, then you are a little bit in a pickle where you have to know how to label and then how to actually input all of these values into your formula. So I highly encourage you to always think about, are you moving with or are you moving against an electric field? And is the charge positive or is it negative? And therefore you will know if it's a gain or if it's a loss of potential energy. Okay, so now I'm going to substitute this into the calculator. okay, and I'll write out the answer. All right, so there you have it. So it's 70.3125 joules in terms of the change. It's positive. You can round it to two significant figures if you want, or you can round to whatever your teachers ask you to. So now moving over to part B. So if you switch over, you notice that in part B, it's asking you for the same exact charge, but it's negative on this side. So therefore, if we had a gain for the positive, then this result would be exactly the same, except it will be negative. So that means that our potential energy, okay, would be lost, so it would be reduced. So we wouldn't have as much potential energy if we were doing that to the negative charge. And that is it, okay? So there isn't anything else. So once you do know in the directions that you're moving, you know, what happens if it's a gain or if it's a loss, which is much better to think about than actually just taking a formula and substituting it in. Because anyone, assuming you're substituting in the right values, can calculate those formulas, right? So it won't be that. The problem will be, you know, is it going to be positive or negative? And then thinking about gaining potential energy or losing potential energy, okay, is worthwhile understanding. And again, look at that video that I pointed out in the beginning of this one, okay, if you have forgotten that concept. All right, so for part C, within here, so we have at what speed would the 0.25 Coulomb charge be moving initially if the final speed has changed by a third from its initial speed? Assume the mass is 1 kilogram for simplicity. Okay, so what happens here? Well, we're talking about the negative charge. So that means we had a loss or a transfer of potential energy to something. Now that potential energy, there is no discussion of friction here, so we'll assume that there's no friction. So we're going to assume that this potential energy has gone into kinetic energy, right? So if it has reduced its potential energy by this much, then by the law of conservation, the kinetic energy must have increased by that much. Okay, so let's write it out. So that means the change in potential energy, so this change, okay, so it has, and I'm going to take the positive, so that means it's a loss of potential, which goes to kinetic, or in other words, you can think of it like this, the change in kinetic energy. So that has to be equal to 0 joules, right? This is by the law of conservation, right? So that the changes are identical, okay, that we have. Okay, or instead of using this formula, I will say that, all right, let's take the magnitude, and the magnitudes must be identical. You know that the signs will be different. One is losing, one is gaining, right? So this was negative, this one would be positive. Okay, so in that case, we will have the magnitude of the potential energy. So all of this, okay, so all of this has gone into the change in kinetic energy. Now, what's the change in kinetic energy? Well, whatever the change is, so kinetic energy final minus the kinetic energy initial, all right? So that's what you would have in there. And if you're writing this down, well, kinetic energy is 1/2 mass, okay, of your V, this is final squared, minus 1/2 mv initial, okay, and this would be squared. Now, they told us that the final speed has changed by a third. So that means it must have gone up, right? Because it's speeding up because the potential energy has been reduced. So therefore, the final one, okay, is higher. So if I write that out, so this is going to be m, instead of writing final, I'm going to put it in terms of initial because that's what we're looking for. So it has gone up by a third, right? So up by a third. So meaning, in other words, it is V initial plus it has gone up by a third. So you can write it like this. This is your final minus 1/2 mv I squared. Okay, so now we need a little bit of algebra. So 1/2 m, this is going to be 4/3 vi squared minus 1/2 m vi squared. All right, let's manipulate this. So this is going to be 1/2 m. Notice I'm going to factor out, this is in both terms. Then in this right here, Well, if you square that, so 4 squared is 16, 3 squared is 9. This is going to be VI squared minus, this is going to be just VI squared. These are like terms because you have the VI squared. You can in fact take the VI squared out. Okay, so if you do that, then this is going to be, so 16 over 9 minus 1, or common denominator, so 9, so 9 over 9. This is going to be just simply 7 over 9 VI squared. All right. And now you can go ahead and substitute M is equal to 1, so that's gone within here. Our change in energy that we had, so this is going to be 70 point, I'm going to just keep all the decimal places within here. So 1/2, so that's going to be 7 over 18 VI squared. And there you have it. So now you can go ahead and solve. So VI squared is equal to, there you have it. All right, so that's how you would solve this one. So this one was an interesting concept that probably might give you a little bit of a headache, but once you see it, you'll know what to do. All right, so thanks for watching. I hope that you found this useful. Bye, everybody.